Good FPGA systems are built to take in, process, and output data at tremendous speed. FPGA engineers work under strict timing constraints to make this happen. In this interview, we will be talking to DornerWorks FPGA engineer Carl Ribbing. Carl, what can you tell me about making sure an FPGA design is properly constrained?
Your tools only really know how how a path is associated to a clock with a constraint. So if you have an unconstrained path, and these are basically paths in your design that the tool doesn't know, how fast that's going to run. The timing engine isn't going to know what to do with that, so it's going to assume that you don't care if it doesn't have a constraint associated to it. So that unconstrained path, they'll put those logic cells, across the path, across the part, because it doesn't think that anything matters with that. So you'll end up with a design that may not work when you put it in hardware. So before you even start with your timing closure, you really need to do an analysis, check to make sure that you do not have any unconstrained paths in your design. And it's really easy with modern tools. The timing tools with your IDE has a place where you can ask it to report out your unconstrained paths, and you should be reviewing those and continuously reviewing those unconstrained paths as your design matures, because you'll have new paths, and you want to make sure that you do not have any unconstrained paths. If there are any in there, you better have a really good reason why that path isn't constrained, because there may be a reason to maybe that path really is an asynchronous signal, and you don't really care about the timing of it. But generally, you want to make sure before you even start timing closure that you have everything covered by some kind of constraint.
How do you approach logic utilization in an FPGA design?
That's another thing that kind of comes early on in your design. You want to really make sure you do a really good job of estimating the size of your design up front, so that you can be aware of, what kind of concessions you're going to need to make with your design, because an FPGA really starts becoming considered full, not 100%, much less. Some vendors say they can take your design all the way up to 100%, but you got to take that kind of stuff with a grain of salt, because you don't know how fast they're talking you can run with an FPGA that's really heavily utilized, and maybe they're talking about perfect pipelining, a perfect design. So you really want to take a step back. As a general rule, anything above 80% full is going to make timing closure much, much, much harder. And definitely when you get up above 90, you're going to be running into some major congestion issues, potentially even unroutable circumstances for some of your nets. So when you get to that point, we all try and architect up front, and we think it's going to have this kind of logic, and we keep adding features as time goes on. You might need to take a step back and think of ways to optimize your design for an area type perspective. You might need to remove features, reduce complexity, so that you can stay below those levels.
What are critical paths, and why are they important to FPGA design?
Yeah, so your critical path in your design, you're going to have a whole bunch of routes that go from flip-flop to flip-flop. And in between those flops, you're going to have some cloud of logic. And this is just your combinatorial logic. They're your comparators, your additions, all the work that you're doing in between your registers. And so you have all these paths that go from flop to flop. And your critical paths are those paths that take the longest, because the paths that take the longest is going to tell you how fast you can run your design. And most designs don't have the luxury of just being able to run at some arbitrary frequency. You maybe you got lucky and and the frequency of the design doesn't matter, and you're able to run it at whatever frequency you care about. And then, that might make timing closure easier, because if you have critical paths that are, too long, you can just run it at a lower rate. But often we're interfacing with external interfaces that run at very specific rates, or we have, throughput requirements that require us to run at certain frequencies. So that kind of fixes the, maximum delays that can go from flop to flop, and that's going to determine how fast we can run. So that's why it's important to analyze your design, find out where your critical paths are, what's limiting your maximum frequency of your design, so that you can achieve timing closure.
How do you analyze your FPGA design to find critical paths?
All the FPGA IDEs have some kind of timing analysis tool, and you can generate reports. And in the options, there's always a section where you can tell it the number of worst case paths to report. Libero with Microchip, they default to 10 paths, which definitely isn't enough. But essentially, you can put in a number here, and that'll report out the worst paths for each clock domain in your design. And then you can review those paths, comparing your code. And if you aren't meeting timing, you can start using timing closure capabilities to reduce those critical paths and allow you to run it at the full rate. So that's there. It's all built in with the timing tools that come with your IDEs.